Thanks everyone for joining me today. So the talk that we're going to cover today is Fable and Foible of Observability and Monitoring. First, a little bit about myself. My name is, sorry, here we go. My name is Jeff Utter, and I work at Warner Media on the Bleacher Report app, backend services and Elixir. And this behind me is my daughter, Olive, and she's important to the talk because she's about 15 months old now, and she's at the stage where she observes and monitors just about everything. Here's a picture of her observing a cupcake. But now back to the talk. So, like I said, it's Fables and Foibles of Observability and Monitoring. What we're going to cover today is a little introduction to why we use observability and monitoring. And then we're gonna go into two stories. One is a story of a success story where we used some monitoring and metrics to make an informed decision on an important configuration change. And the other story, it's not a complete failure, but it's a word of warning about observability and monitoring. So first off, why do we use observability and monitoring tools? We can use them to find bugs. We can use them for performance monitoring, find bottlenecks in our application, and auditing. Now, all of these are in the context of running production applications. You may be able to use these in your QA environments or staging environments, but where they're really useful is when your code meets that production traffic that you can only get in production. Now, to collect metrics, we have some libraries and tools in the Beam ecosystem. This list is by no means exhaustive. We have Beam telemetry, which comes into play in most people's solutions for this. Statics, which exports stats metrics. OpenCensus, which does tracing. I think either it also supports metrics or there's plans to do so. Spandex, which is also for tracing, but its main use is Datadog. I think it's pluggable, but we use it in conjunction with Datadog. And then there's Prometheus and Promex if you're exporting things to Prometheus. The bolded ones are what we use on Bleacher Report. They are by no means any better or worse than any of the other options. We've been doing this for a while, and some of these other options didn't even exist when we started. So this is the stack we've settled on. Once you've collected the metrics, you need some way to look at them. We use Datadog, which provides visualization for both metrics and tracing. There's other options, some open source ones being Jaeger for tracing and Grafana for metrics. If you've never seen traces before, this is an example of a distributed trace. I've zoomed it out so you can't necessarily see what's being traced here, but if you've ever seen a flame graph, it sort of works like that. Time progresses left to right. And in this case, the traces are top to bottom. Usually in flame graphs, they're visualized the other way around. But you can see over the lifetime of a single request, you can see some functions that it hits. You can see maybe some asynchronous tasks that were processed, requests that went into other applications entirely, and then what they did in that other application. You can kind of get an overall view of all of this, everything that goes into one request. In this graphic specifically, the purple, dark purple, I think are tasks that spawned within one Beam VM. I think yellow is database queries, and the other purple color I think might be distributed traces. We'll also see some graphs made off of metrics. We'll hit some of those later. But first up is our first story. This is our fable. I call it the Pied Piper of Ecto database pools. The town of Sports News was being overrun by database connections. And we had this pretty horrific looking graph. Now I'll show this graph again later with axes and legends and some more details. But essentially what's going on here is we had a traffic spike that increased our traffic so much that our database pools couldn't keep up with the amount of requests coming into the system. And maybe you've seen these type of errors before. They look like this. DB connection error, connection not available, and request was dropped from queue after some number of milliseconds. I won't read the rest of the message, but maybe these are familiar to you. What this is saying is that, so with a database pool, you can handle so many requests concurrently, And if more requests arrive in your system, they wait and they queue. And eventually, Ecto, or I guess it's actually DB connection, will drop them if they've waited too long. So rather than having them, pile up for forever. So that's what was happening here. We had so many requests coming into the system that the pool just couldn't handle it. So this brings up a question, I guess a problem, is how do we optimize the size of our pool? How do we find the right number of connections? If we have too many connections to the database, this adds load both to the application for maintaining the pool of connection and kind of record keeping, but also to your database. In Postgres, each connection uses about 1.5 to 14 megs of memory per connection. So if you have 1,000 connections to your database, that's like almost 1.5 gigabytes of memory used in the database just for your connections. That doesn't include whatever you're doing with those connections, any queries, loading any tables, keeping indexes in memory or anything like that. If you use too many connections, you can run out of connections. A lot of databases and database vendors set limits to the number of connections to kind of stop you from shooting yourself in the foot like that. You can usually tune these settings, but they're there for a reason. So you can run out of connections, and then every time you try to make a request, whether the database is overloaded or not, you'll get errors about not being able to get a connection. On the other hand, if you have too few connections, it just adds increased latency and unnecessary wait time to all of your requests. For example, if you have a pool of 2 and you have 5 requests arrive at your system at once, 2 of those requests will go and process in the database immediately, but the other 3 will have to wait for that to finish. And if your database has the capacity, you could have sent those requests along and they could have been served without waiting. So to find the number of database connections, in Postgres, we can use the select count star from pgstat activity. If you're using a hosted database like RDS, there's usually metrics in the console. For us, we get those RDS metrics exported into Datadog, so we get a metric like aws.rds database connections. So let's look at this graph again, now with some details. So the purple line is the number of connections we have available per instance, and the red bars are the count of those errors that we saw before. Now the axis for the connections is logarithmic, so it's like somewhere around 20 connections per instance, whereas the axis for errors is linear. But we hit somewhere like 600,000 errors per 5-minute block or something like that. And what's happening here is about halfway through, we got a spike in traffic, like I said, and the number of requests coming into the system outpaced what we could handle, and we start getting those errors. So we set this number 20 sort of arbitrarily, maybe through some trial and error or discovery, but I think we can make a better informed decision on this. And we can use everyone's favorite queuing theory law, Little's law. And this is expressed as L equals lambda times W, where L is the average number of items in the queuing system. Lambda is the average number of items arriving at the system per unit of time, per second or whatever. And W is the average time that an item spends in the queuing system. To break this down a little bit more, we can use specific metrics. So for the average number of items arriving in the system, we have this metric called ecto.query.count. Now, if you have some solution for monitoring and metrics, yours may be named differently. But what this is just a counter that every time a query is made, it adds 1. Database lets us, or Datadog lets us bucket these in time windows, like we can answer questions like how many requests per second. The average time, so W, which is the average time an item spends in the system, we have this metric ecto query total duration microseconds. And that's just the average time a request spends from when it enters the system till it's completed the database transaction. And then L is essentially just the product of those two. So if we multiply the count of queries by the average time they spend in the system, we get this other number L, which tells us if we never want to queue, if we always want to have available capacity, we essentially just need more than L pool connections. So back to our graph here. Now I've added this blue line to the graph, which is the number of connections required. This is that calculation. And we'll see on the left side of the graph, we still aren't providing quite enough connections. And I can tell you that we're probably still queuing just not to the point of erroring. You'll see there's a few red bars on the left there. So those points in time did error. But for the most of the time, we're not queuing to the point of erroring, but we're queuing a little bit. We don't have enough pool connections available to service all the requests. Now, when we get to the second half of the graph, there's our nice friendly red lines again. And you can see the number of connections that we would have needed to not queue is significantly larger. It hits something like 150 while we're giving it 20. And then, so using that information, that calculation and the metrics from that, we can come up with a better informed number of connections to use. So here's another, this data is from a little bit later in time, but we can see initially we had more connections. Again, it's at 20, but we required maybe 10 or 9. And we had about 20 available. And then as time goes on, we get another traffic spike that, again, we don't have enough connections available. And eventually we tune the purple line, which was the number of connections per instance, up to about 50, I think. And then the errors go away and there's no or very little waiting involved. Now for us, that number is static. We just set this application gets X number of pool connections per instance. I've considered a system where that's calculated dynamically using Little's law. You could say, you know, we're getting this many requests and they each take this long, so we need this large of a pool. I think though, with that, you could end up in some bad situations. Like I said, having too large of a pool adds overhead, both to the database and the application. So you could get into a situation where if you need more connections, you add more connections, which in turn increases the latency. So the average time things spend in your pool is larger, which means you need more connections, which increases latency. And you can see that kind of spirals out of control. You could maybe make something smart if you could set some bounds, but ultimately you would need your database to scale automatically as well, which most databases don't do too great, to keep that latency down when you add the pool connections. So there's no free lunch. Having too large of a pool puts CPU load on your application and database. So sometimes queuing and dropping is what you want to do. You want to have that back pressure, that load shedding to say, these requests aren't going to finish fast enough. We'll toss them out before things get too bad. However, the moral of the story here is you can look for interesting ways to combine your metrics to make informed decisions. Like I said, there's no silver bullet for this particular problem, but the alternative would have been randomly picking another number. Let's try 30 instead of 20 and see how that goes. So this gives us a better baseline to start from. Now we're going to take a little break from our regularly scheduled fables and talk about a library. We use this library. It's an internal library right now that we're hoping to open source soon. It's called Hertz. And although it's an internal library, the concept I think is really valuable, which is why I'm sharing it with you today. This library gives us unified metric collection and reporting across services. So we have many services in Elixir, and this library allows us to automatically instrument a lot of our the other common libraries we use, like Ecto and HTTP clients and whatnot. And A, instrument them automatically, and B, have consistent naming and units across those metrics. Now, this library specifically for us uses beam telemetry, statics for statsd, and spandex for traces. So if you don't use that stack as a library, it might not be so useful, but I'm hoping the concept is useful. This is how we essentially start it. This is an application supervisor. You can see there's a worker in here called Hertz, and it has a list of monitors, one for Ecto, one for HTTP, which handles both Phoenix and Cowboy, one for Redix, and one for Finch. And that's all that we need to start up these monitors. And like I said, it gives us consistent naming across the metrics. So application A doesn't name things one way and application B names it a different way. It also makes it a little bit easier to discover these metrics because A, if we need to know the names, we can just look in the source code of this one library, and B, they're kind of predictably named. It also helps with, since they're named the same, to compare metrics across applications, like comparing request rates or anything like that. It also makes it easy to aggregate metrics across the application since they're all named and tagged similarly. Those monitors from the previous slide look something like this. They're really simple. It's a module with an install function. that for most of them just sets up our telemetry handlers. And then below that are the telemetry handlers. The install function could do other things like maybe set up something that runs on an interval to collect beam stats or something like that. But for the most part, they're just simply setting up telemetry handlers. And then in the handlers, the details here aren't terribly useful. We're naming things and tagging them in a specific way. But the important part is like on the last line where we have tracer.startSpan Redux.pipeline. So every application that uses this monitor is going to have spans named Redux.pipeline. You don't have to worry about people using different names in different applications. And the final benefit is it kind of removes the excuse of like, oh, well, I didn't have time to add metrics to this application or whatever. You just have to drop the library and it works. So that library, whether it's released as a library that you can consume as a library or just the concept, I think is very useful to everybody. And if you have more than one application, I think it's worth the investment to build something like this. Now back to our stories. It's time for our foible. I call this one Goldilocks and the two bottlenecks. Once upon a time, there was a developer named Jeff. And he decided it would be a good idea to upgrade to OTP 24 and came upon a strange performance degradation. Now, I've given another talk recently where I talked about the same overall problem, but I'm going to be approaching it from a little different lens. So hopefully it won't be a repetition for anybody. This is what the degradation looked like. The latency for this service, and this is P95 latency, was about 5 milliseconds. And then we get a traffic spike and it spikes up to like 700 milliseconds, which is not great. That only lasts for a couple minutes. And then it comes back down, but it drops down to 50 milliseconds. It never returns to 5, even when it's idle. It's really strange. See the same thing for CPU. It's about 40% CPU usage, spikes up to 140, and then drops back down to 90. It never returns back down to the baseline that it should have, even when it's idle. Now, I did a bunch of upgrades when this happened. I could go back and downgrade all the libraries and add them back one at a time and figure out what caused this. But this error happens super infrequently, generally during Sunday night football, which is not when anyone wants to be debugging things. But it's hard to reproduce and it's hard to catch in the act. So I could, downgrade everything, upgrade them one at a time, but it might take weeks for each individual upgrade to say, was this the one that caused the problem? So I think that's okay. We've got a really good VM with great tools for introspection. I can figure out what changed and what's using my CPU now, right? So the first thing I reach for is Observer CLI, and I look at reductions. If you don't know what reductions are, they're the count of function calls per process. It's kind of the closest thing we have on the beam to CPU usage. You can see which process is doing the most work. Now, if you look at it in Observer or Observer CLI, this is how many reductions that process has had since it was started. So for the case of the top one here, which is Logger, that's since the beginning, since the beam was booted, which is maybe not always the most useful. The better option is to use the recon library by Fred Hebert. It has this proc window function that'll let you say, I want to know the top 5 processes for reduction usage over 10 seconds. So it measures all the reductions in all the processes in your system, waits 10 seconds, measures again, compares, and shows you the top 5 offenders. Really useful function in this library. Now, I did that, found out Logger was still the top culprit here. Why is our Logger using so many reductions? Well, our Logger does a little extra work. We have a custom logger that does some filtering to keep keys and secrets and things out of the logs. And we also were logging all successful HTTP requests, which for this service is a lot. Now, to make things worse, when we start getting these database timeout errors, that generates a bunch of logs, which go through the logger, which takes CPU usage, which puts more load on the system, which causes more things to time out, which causes more logs. And you can see how that kind of spirals out of control. So the easiest thing to do here was to add probability to our logger to not log all of the successful HTTP requests. And that looks like this. We have our plug logger. It's custom. It's built into that Hertz library. And for all the log levels, we can provide a sample probability. So in this case, the probability, if it's a debug level log, log it. If it's info, only log 5% of them. Warning, always, error, always. And the implementation is super simple. We get the log level, and that keyword list of probabilities. We pop the probability out for that log level. If the probability is 1, go ahead and log it. Otherwise, generate a random number. If it's greater than or equal to the probability, we don't log it. And otherwise, we do log it. Now, this bottleneck, it was too small. It just kind of kicked the can down the road a little bit. It still was running into that problem less frequently and maybe less severely, but it was still happening. So back to Observer CLI, and this time we look at message queue. And this one process, it was pretty busy. Elixir Spandex Datadog API server had 108,387 messages in its inbox. This process is used for sending spans and traces to Datadog. And this was just a random instance. And the message inbox had 108,000 messages just sitting there. It's probably worse on other instances too. Now, I dug into what this process was doing a little bit. And it's used for sending traces to Datadog. And it has a single process bottleneck in the path of every request. Whenever any request finishes, it makes a call into the Spandex Datadog API server, which has to be serialized. So every request in the system has to go through this. Now, it's generally pretty fast, but when we get a ton of requests, it can slow down. And it also sometimes it flushes the buffer, which adds a little bit more latency to one call. So it quickly backs up. And this is okay. It's like, I don't want to trash talk this library or anything. It's worked great for us for a long time. And it also allows us to swap out that API server. So we can provide our own with a different implementation, which is really great. So like I said, we can provide our own implementation. So what I ended up doing was writing a new implementation that was improved for write concurrency. So all the writes when requests finish can happen concurrently. There's no lining up in a queue in the message inbox. To come up with a solution for this, I looked at the OpenTelemetry OTel batch processor, which has a really clever solution. Don't have time to dig into it deep, but essentially the way it works is there's two write concurrent ETS tables. Whenever a request finishes, it writes the traces into the ETS table. And after a certain interval of time or a certain size of the ETS table, it will change a persistent term that tells it to start writing into the other ETS table while the first one flushes. If we get into a situation where we're getting so many traces that it can't flush and it has to switch back and it isn't done yet, we just disable writing these traces altogether. So now sometimes we drop traces, but our app continues to work and doesn't get in this like perpetually backed up state. Now, you might say dropping traces doesn't sound great. Like I want that information. And we even have metrics for how many traces we drop. And this looks like not great. We're dropping a few hundred, like 600 over a few minutes. But over the course of a day, and this is just an average day, we insert about 147 million traces and dropped about 3,000, which is 0.002%. That's a percentage I can live with. And I think even the old implementation, although we didn't know it, was losing traces because they were sitting in that message inbox and timing out before they could get processed. Now at least we know what we're losing, right? There is one improvement I think we could make. We could prioritize the error traces. I generally think error, information is more valuable than the success information. The success information is useful for looking at latencies and whatnot, but I think, if we had to prioritize something, we could prioritize the error traces and drop them less. So the moral of this story is that observability has overhead. We need to use it intentionally and use it carefully. So in conclusion, we've looked at two different stories. One shows us that we can look at our metrics in interesting ways, find different ways to combine them, maybe apply a little bit of math, and come out with new metrics that are potentially more valuable than the ones we started with. And also that observability has overhead. We need to use it intentionally and use it carefully and be aware of its implementations and the trade-offs that make. I think we're out of time. I don't really have any time for questions. So that's it. That's the end of the talk. Thanks for joining me. If anyone does have questions, I can answer some questions in the Whova app or over Twitter, and I'll try to drop into the Toucan chat later. So thanks for joining me. Hope you all enjoy the rest of the conference.